Now that we're familiar with the idea of a basis for a vector space, let's build on that a little bit. We're going to talk about the idea of coordinate systems, and we're going to use bases to get different coordinate systems for a vector space. So let's start off with the basis. I've got this one right here, 2, 0, 1, 2, which obviously is a basis for a particular known vector space, particularly R2. It's two linearly independent vectors from R2, and we know that 2, their span, is enough to span all of R2. Okay, so that's a basis for R2. And we could do things like say, where do you get if you take 3 of the first one and 4 of the second one? So we could do something like, what does 3 of the first one and 4 of the second one get you? Where does it get you to? You can work that out numerically, and you can also sort of think of it graphically, but let's do numerically first. Let's see, that would be 6 plus 4, that would be 10, 8. Get you to the place in space that we know as 10 over and 8 up. So that's numerically. Graphically, again, of course, you can think of this as having a vector called 2, 0. So let's do 2, 0 in red. So 2 over, oops, there's 2, 0. And the other one was 1, 2, so 1 over and 2 up. And let's do that one in green, 1 over 2 up. Oops. Looks about like that. And what we just did was take 3 of the red vector. So we did 1, 2, 3 of the red vector, and onto that we added 4 of the green vectors. And keep in mind, when you add vectors, you go tip to tail. So 1, 2, 3, 4, and we ended up right there. And again, in normal coordinate space, we would say we ended up going 10 over and 8 up to get there. You could also say that we went 3 of this and 4 of that. That would be another way to describe where we went. And we call those coordinates. So we'll call those coordinates in this basis. So there's a little bit of notation that goes with that right now. But for the moment, let me just say we've sort of got 2 ways to describe this point here in space. We've got standard coordinates, I guess you would call it, which would be, say, 10 over and 8 up. But we've also got these new coordinates that refer to our basis, our new basis. And the coordinates are really 3, 4. I say 3 of the first basis vector, 4 of the second basis vector. Let me point out, by the way, that the standard basis, they sometimes write with a funky cursive E. It's just 1, 0, and 0, 1. And we could get to that same point, of course, in standard coordinates, standard basis. This same point we could get to by doing 10 of the first one and 8 of the second one. That would also get us to that same point. It's using different basis vectors. And it's basically saying take 10 of 1, 0. So 1, 0 looks like this. So take 10 of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. and then take 8 of the 0, 1. So 8, 1, 2. I mean, this is just basic XY coordinates, right, that you learned in 3rd grade. 1, 2, 3, 4, 5, 6. I'm not quite to scale. 7, 8. Anyway, that's how we've always done coordinates. That's graph paper. And really, all we've gotten with our new coordinate system of 2, 0, 1, 2 is we've gotten graph paper that's not little squares, it's little sort of slanty parallelograms instead. You can move in the red direction or the green direction instead of 1 over and 1 up like you did on regular graph paper with the black vectors here. So what I've got so far is 2 different bases for R2. So I should point out, this is also a basis for R2. We learned in the last couple sections that bases are not unique. You can have multiple different bases for R2. For instance, we've got 2 different ones right here. And there's a lot more. As a matter of fact, we could do another one if we wanted to. But in each of those bases, there will be coordinates to get to the same place, or to describe the same place. Let's just do one more right here. And I wasn't even planning on doing this, so I'm just making this up off the top of my head. Let's see. I'm going to make up a new basis, C. And let's see, what should C be? Let's go -2, 4, and and 2, 1 for lack of creativity. Okay, there's a new basis. This one is 2 linearly independent vectors. So it's also a basis for R2, which means I should be able to get anywhere in 2-dimensional space, including that point right there. So my question for you is, what are the coordinates in C that will get us to this same point? I already know the coordinates in B, 3, 4, 3 reds and 4 greens. I already know the coordinates in E, 10 black vectors and 8 other black vectors. So now I want the coordinates in C. So I'm going to ask you, I think you should be able to figure this out. I'm going to ask you to pause the video here for just a second, see if you can work out the coordinates in C that get you to 10, 8, and then come back and we'll do it together. All right, did you get it? Since this was an example I just made up, of course it didn't come out whole numbers, but if you didn't get it, let's walk through it together. Let's just say that. I'm sure you got it. So we're looking for, some multiple of -2, 4 plus some multiple of 2, 1 that gets us to the same spot. That gets us to 10, 8. And you can rewrite this a couple different ways, but ultimately, you could write it in matrix multiplication form. This is currently sort of in vector form, or even linear equation form, but ultimately you're going to solve this system either with an inverse matrix or with row reducing. I'll just go ahead and do row reducing. So augmented matrix. And you can do that with a matrix calculator. Of course, it's actually not too hard to do this one by hand, although there are some fractions involved. And it comes out 1, 0, 3/5 and 0, 1, 28 fifths. So again, it's our old friend row reduction that tells us how to get there using these 2 particular basis vectors. So it should be 3/5. You know what? I should actually use my eraser. Look at that. I can erase things. Okay, so it should be 3/5 of the first one and 28/5 of the second one. And we can just check and make sure that works out. 3/5 times -2 is -6/5 plus 56/5 is 50/5, which is 10. And on the bottom, 4 times 3/5 is 12/5 plus 28/5, 28, 38, 40/5, which is 8. Okay, good. It's fine. It works. So we now have the coordinates for this same point in 3 different coordinate systems. So all a coordinate system means is a different basis. So you say in basis B, it was 3 of the first vector and 4 of the second vector to get there. In basis E, it was 10 of the first and 8 of the second. I don't know if you can hear my cat. He's saying hello to the hummingbirds. And in the C basis, it's 3/5 of the first vector and 28/5 of the second vector, all to get to that same point. So a little bit of notation to close out this video, and then we'll do the rest of it in the next video. So we do want to say that coordinates depend on what basis you're talking about. So when you say 3, 4 as a set of coordinates, you need to know what 3 of what and 4 of what, right? What are your basis vectors? So we have a little notation where we put this sub B on there. Sorry, my cat is going nuts. Okay. And you would then say that's equivalent to or equal to 10/8 in basis E, which is equivalent to 3/5, 28/5 in basis C. Those are 3 different coordinate systems to get to the same point. Eventually, we are going to want to be able to go right from basis B to basis C without having to take a stop in the middle for basis E. But that is a different day. That's not 4.4. We do have a little more to talk about in 4.4, but we'll do that in the next video.